got momentum.
Napoleon, I mean, you're 5'9", 185 pounds. I mean, you don't have the momentum of, say a Dorsey Levens.
Hey, man, I got momentum.
Napoleon, listen, if it were up to me, I would say yes, but it's not me, it's the big guys. You know, the suits at the network, they're telling me I gotta do a show on momentum. I gotta find a running back with momentum.
I got momentum. Sports Figures, put your brain in the game.
Usually when we think about collisions, we think about cars, right? But obviously collisions are a big part of football, too. Collisions are also a big part of science. In physics, whenever two objects come together, we have what scientists call a collision. Now, collisions can be big or small. But whenever two objects come together, we have a collision. And you can't have a collision without momentum. Size is pretty important in football, right? Like if I weighed 500 pounds, I could probably move this thing pretty easily, because I'd have a lot more weight to throw at it. We see this in football all the time. That makes sense, right? Something heavier smashes into something lighter, and the lighter object moves. That's because the heavier object has more momentum. So, how do you explain this?
Napoleon only weighs 185 pounds. The defender weighs 310 pounds. When the two of them collide, how could Napoleon ever score?
How could a smaller player have enough momentum to push back a giant defender and score? This guy back behind me is a pretty heavy-duty object. His name's Napoleon Kaufman, and he's a running back for the Oakland Raiders. Last year, he broke Bo Jackson's team record for yards in a game with 227 yards on 28 carries. At 5'9", 185 pounds, he's on the smaller side for an NFL back. So how does he take the pounding from all those defenders? What are some of the advantages and disadvantages to being a smaller back in the NFL?
Well, I say the advantage is, you know, sometimes considering how big the linemen are in this league, you know, we can kind of hide behind the big guys, you know, and another thing is the speed factor. You know, a lot of the linebackers, they're just, now there's some that are fast, but not as fast as some of us. So it definitely plays to our advantage.
I guess you never get caught, right? You just blaze past these defenders all the time?
Oh, no. That's definitely not the case. You know, obviously lining up most of the time 6, 7 yards deep, you have to, you know, generate enough momentum to plow into these guys and break tackles. And, you know, a lot of the small backs are really doing that lately because of the speed factor and because of the fact that, you know, we get a chance to get a head start at the guys.
Right, get some steam going.
Yeah.
Momentum is around us all day, every day. Now, if we have more than one momentum, we call it momenta. That's plural for momentum. I have momentum. Now I don't. You see, momentum is sort of like the quantity of motion. And part of it is how much an object wants to keep moving. And the more momentum you have, the harder it is to stop. And the more it hurts when something stops you. A little momentum and a lot of momentum. The quantity of motion, momentum. When something big and heavy is coming right at us, we know instinctively that it's got a lot of momentum. And we know to get out of the way.
That's why most football players are so big.
Their bigger size gives them greater momentum when they're moving.
Well, what if I told you that this bowling ball and this soccer ball could have the same momentum?
No way.
way, Marquez. I'll show you. How was that?
Not real hard. It was going so slow that it didn't have much momentum.
Okay, I'm gonna try the soccer ball, all right? How's that?
About the same as the bowling ball.
Okay, they had the same momentum, so what does that tell us?
It was going faster, so momentum depends on both speed and mass.
Correct. In an equation, it looks like this.
P, momentum, equals mass times velocity. So the amount of momentum an object has is a function of both its weight, its mass, and its speed, its velocity.
Oh, this is what momentum looks like in an equation, a lowercase p. Now, why a p? I have no idea. You just gotta memorize that. P equals momentum. P equals momentum. P equals mv, or mv equals p. MVP, get it? Now I have momentum. I have mass and I have velocity, so I must have momentum. And we can figure out my momentum really easily. We just have to multiply mass by velocity. Now, here's something really sick about momentum. If there's no outside force to change it, the momentum stays the same. Momentum just keeps going and going forever. That's called the conservation of momentum. And in physics, that's a law. Momentum must be conserved. Now I don't have momentum. I'm stopped. Well, what happened? An outside force affected my momentum. In this case, it was the friction of my wheels. Friction is a force that affects momentum. Because momentum is conserved, it can be passed from one object to another. The momentum is passed from one ball to the next. Now, with no outside force to affect it, the momentum can go on forever.
When a player in motion hits a stationary player and they stick together like this, they become one object. That's called a sticky collision. The momentum stays the same, but now they have a greater mass because they're two of them.
But it seems like your momentum is less after you make contact.
Actually, Napoleon, it's your speed that's less. Your momentum stays the same. Now, we can figure it out with just a little math. We're gonna multiply kilos by meters per second.
Football is pounds and yards. Forget all that metric stuff.
Yeah, but you see, if we use pounds, we have to figure it out with slugs.
Slugs?
You don't want to know.
Yeah, let's just stick with the metrics.
We can find a number for the defender's momentum before he makes the tackle and after he makes contact. We know the defender's weight, 290 pounds or approximately 130 kilograms. To find his velocity, we'll use the video frames. Each frame is 1/30th of a second. The defender is moving a foot for every 30th of a second, so 30 feet a second or 9 meters per second. So we have mass and velocity. Multiply and we get momentum, 1,170 kilograms meters per second. Now look what happens after they make contact. Because they stick together, they're now moving as a single mass. We add the defender's mass and the running back's mass to get a new mass of 214 kilos. That's 471 pounds. We figured out their velocity, 5.467 meters per second. So if we multiply our new mass by our new velocity, we get 1,170 kilograms meters per second. The same momentum we had before.
The momentum is conserved. The momentum before a collision is the same after a collision.
That would only work if the quarterback had no frictional force against the ground.
Right, but for that model, we'll say he didn't. If he did, the momentum would be reduced by the amount of friction. But because there's no outside force, the momentum stays the same. On a football field, it's usually both players who are moving, right? Well, let's say we had two players with the same mass, and they hit each other with exactly the same velocity in opposing directions. What would happen? Let's go to the Sports Figures blackboard and take a look.
Anytime a defensive lineman and an offensive lineman go head-to-head, you have a collision of major league proportion. Weighing in the neighborhood of 300 pounds each, these players carry a lot of momentum. So, what happens when they meet? They both get off the line equally well, so their velocity is the same when they meet. The offensive lineman has momentum in this direction. We'll call that positive. And the defensive lineman has momentum in this direction. We'll call that negative. When two objects collide, we can take the sum of their momentum to figure out what's going to happen. When they hit head-on, we add their two momenta to get 0. They stop. Two big players, one big collision. You add them up, you get one big 0. Their equal and opposing momenta cancel each other out. It's all in the numbers. I'm Mark Malone at the Sports Figures Blackboard.
All that stuff works when you hit each other head on, but most of the time it's not that way. We hit each other at angles.
Right, but the momentum is still conserved. So, Napoleon, what happens when you're running and a defender hits you at an angle?
Well, usually we keep moving, but in a different direction.
That direction is the sum of your two momentums, yours and the defender's.
Napoleon has momentum, and he gets hit at a 90-degree angle by a defender.
Okay, so what do we got here?
Napoleon had momentum in this direction.
Huh?
The defensive back had momentum in this direction.
And when they collided, they went off into this direction.
Right. Now, because they hit at an angle, we can't simply add one momentum to the other like we did when they hit head-on. Now, to figure out momentum in different dimensions, we use arrows like this. They're called force vectors. Okay, this arrow here represents the sum of our two momenta. That's our two momenta added together. Kong, what if Napoleon and the defender had exactly the same momentum?
They would have gone in this direction.
Right, but they didn't. So what can we tell about their momentum from our vectors?
Napoleon had a greater momentum because they went more in the direction his momentum was going in.
Correct. Now, you can use vectors like this to figure out exactly what the relative momentum for different objects were before a collision. That's what this gentleman does for a living. This is Steve Lovell, and he's a traffic investigator for the Oakland Police Department. So, Steve, how do you use physics in police work?
I recently investigated this accident. It's coming off a residential roadway. The driver said that he stopped at the stop sign, proceeded in the intersection, and then struck this car on the side. Well, based on the weight of the car, the weight of this vehicle, the angles of approach and angles of departure, using momentum, I can actually calculate the driver's speed to find that he's not all truthful when saying he stopped at that stop sign.
Now, Napoleon, you weigh...
About 185 pounds.
Okay, so that would be 83 kilos. So we're going to increase your momentum with...
Velocity.
Right.
Napoleon hits the line of scrimmage at 3.66 meters per second. 83 kilos times 3.66 meters per second is 303.8 kilos meters per second. That's a lot of momentum.
And because I weigh less, I can get up to speed faster because my inertia is less.
Inertia. Well, Napoleon, you've been studying a little physics, haven't you?
A little.
So, what did we learn?
That momentum is like the quantity of motion.
Right.
And that we can find a number for momentum by multiplying the object's mass by its velocity.
Correct.
And that momentum is conserved, the law of conservation of momentum.
Right. That's right. That's right.
That means that momentum will continue until acted upon by some outside force.
Okay.
In the collision, we can add the two momentums.
Okay. All right, that was great. Oh. Well, I'd like to thank Napoleon Kaufman and the Oakland Raiders.
I got momentum.
And of course, our students, Marquez, Mohammed, Veronica, Asha, and Kong. Officer Steve Lovell of the Oakland Police Department for helping us out today on ESPN Sports Figures, Running with Momentum.